Hello, this is problem set number 3, problem 4. The engine of a Ferrari F35 F1 sports car takes in air at 20 degrees Celsius and 1 atm and compresses it adiabatically to 0.09 times the original volume. The air may be treated as an ideal gas with gamma equals 1.40, right? Gamma is a ratio of molar heat capacity. Okay, so for part A, draw a PV diagram for this process. Okay, so part A, well, let's first write down what we know. We know that the initial temperature is 20 degrees Celsius, right? The initial pressure is equal to 1.00 atm, okay? And it is compressed, so we know that V1 will be greater than V2, right? Because it's compressed. And it's an adiabatic process, right? So adiabatic, which means no heat transfer. So Q equals 0. Yep. And compresses it adiabatically to 0.09 times the original volume. Okay, so they don't really give you a specific number for volume, but I know that my V2, my final volume, is 0.09 times my initial volume, or V1. Yeah. Okay, the air may be treated as an ideal gas with gamma equals 1.40. So gamma is 1.40. Remember, gamma is just a ratio of molar heat capacity, right? So gamma is equal to the Cp over Cv, okay? And that's the molar heat capacity for constant pressure over molar heat capacity for constant volume. Okay, you don't really need it for this problem. I just wanted to remind you guys that. Okay, so for part A, let us draw a PV diagram for the process. Okay, so that is my PV diagram. This is volume. This is my pressure line. Okay, so I know that V1 is greater than V2. Actually, so I'll put, here's my V2, and this is my V1, right? I know P1 is at 1 atm, so it's P1, that's 1 atm. I don't really know my P2, so I don't know actually if P1 is, or I don't know the value of my P2, right? But because this is an adiabatic process for an ideal gas, let's know that there are two equations that we know we can use for an adiabatic process for an ideal gas, right? And that is P1 V1 gamma is equal to final pressure times final volume to the power of gamma, okay? So that's the first equation I know I can use for an adiabatic process for an ideal gas. The second equation is initial temperature times initial volume to the power of gamma minus 1 is equal to the final temperature times the final volume to the power of gamma minus 1, right? Okay, so that's something that we should know, and it came from our notes. And ideally, would be in your cheat sheet, okay? This is for adiabatic process of an ideal gas. That is chapter 19.8, section 8, 19.8. Okay. So I'm going to use this first equation right here to find my second pressure, my final pressure, because I don't know where the state is for the final state because I don't know my pressure. So I know my P1. So if P1 V1 gamma is equal to P2 V2 gamma, I know my P1 is 1.00 ATM. My initial volume, I actually don't know that, but I know it's, let's just call it V1, right? And gamma is 1.40. Right, that was given to us. That's equal to my final pressure, which I'm trying to find, times my final volume. I don't know the exact value of my final volume, but I know it's 0.09 times my initial volume. And that is the power to the power of gamma, which is 1.40. Okay, so using algebra, I can find my final pressure. That will be 1.00 ATM times my initial volume to the 1.40 over 0.09 V1 to the power of 1.40. Okay. I could obviously rewrite that. That's basically just 1.00 ATM multiplied by V1 to the power of 1.40 over 0.09 V1 to the power of 1.40, right? And actually, when we have something like x to the, let's say, 16th power over a number y to the 16th power, that's the same as saying x over y to the 16th power, okay? So I'm going to use that rule for our volume, okay? So I can rewrite that as equal to 1.00 ATM times V1 over 0.09 V1 to the power of 1.40, right? And we'll see that our V1 can cancel out from the numerator and denominator. And I'm left with 1.00 ATM times 1 over 0.09 to the power of 1.40. Okay, so plug that in my calculator. I'll find that my P2 is equal to 29.11 ATM. Okay, so now I know where, I know that the value of my final pressure. So P2 will be somewhere here, right? A lot higher than 1 ATM. So let's draw our PV diagram because now we know the value of the initial state and final state. Okay, so my initial state is V1, P1 right here. That's state 1. State 2 is V2, P2 right here. And my curve will be, it will go like that, in that direction. Okay, so that is my PV diagram for this process, the path from state 1 to state 2. Okay, now part B. Part B, find the final temperature and final pressure. Oh, okay. Well, we already found the final pressure here in part A, right? That's this guy, our value right here, we know it's 29.11 ATM. So actually we already answered part of part B. So now let's find final temperature. So find final temperature, TF, and final pressure, PF. Well, we just found the final pressure in part A, so I'll just write the answer. Final pressure is 29.11 ATM. Okay. And final temperature, I will use this second equation I have right here, okay, to find my final temperature. And for the final pressure, I use the first equation, right? Okay, so final temperature for this, I know that the equation T1 V1 to the power of gamma minus 1 is equal to T2, or final temperature, times final volume to the power of gamma minus 1. Right? Again, gamma is the value of the ratio of heat capacity. And in this case, it was given as 1.4. All right, let's plug in our knowns, the things we know. We know initial temperature is 20 degrees Celsius. However, to use it for this equation, I need to convert it to Kelvin. So I'm going to add 273. So in Kelvin, that's 293 Kelvin, right? Okay, so I have 293 Kelvin as my initial temperature times my initial volume. Again, that is just, we'll call that V1. And gamma is 1.40 minus 1 is equal to final temperature, which I'm looking for, times final volume, which I know is 0.09 times my initial volume, and to the power of gamma, which is 1.40 minus 1. Okay, so I'll rearrange this for T2. So that becomes T2 equals 293 Kelvin times V1 to the power of 1.40 minus 1, that's just 0.40, right? Divided by 0.09 V1 to the power of 0.40. Again, that's 1.4 minus 1, this exponent. All right, that will be the same as saying 293 Kelvin multiplied by V1 over 0.09 V1 to the power of 0.40, right? Same thing we did up here, because they have the same power, right? We just write them like that. Okay, so my V1s cancel out. So I'm left with 293 Kelvin times 1 over 0.09 to the power of 0.40 as my final temperature. Okay, and if I plug that in my calculator, I get that my final temperature is equal to 767.66 Kelvin. And that is the final answer for part B. We have final pressure and final temperature. All right, thank you.